Now let's make this a little bit more realistic. We'll add friction to the system. So let's suppose our surface is replaced with something from frictionalsurfaces.com, and it has a coefficient of sliding friction of mu equals 0.05. What does that mean? Well, mu just tells me what to multiply by the normal force to get this frictional force. So my frictional force here will be 0.05 times 400. Now I know 0.05 is the same as a 20th, 20 nickels in a dollar. So a 20th of 400 is 20. So I have 20 newtons of friction acting on this guy, on the red artichokes. And over here I have also a frictional force. This is a quarter as heavy, 100 newtons versus 400, so I'll have a quarter of the frictional force. How am I getting that? I'm taking 0.05 times the normal force of 100. 5/100ths of 100 is 5. So if I redo this problem with friction, here's what I see. I have, for my pickles, acting to the right, and therefore positive, is the tension. I'm reading this diagram. Right is positive, left is negative. T minus 5, that's my net force. That's equal to this mass times its acceleration. What is this mass? It's 10a. And notice, this is a pattern. This side of the equation doesn't change when I add friction. For my artichokes, I have pulling to the right 80 and pulling to the left 2 things. So these will both be negative. So I have 80 minus 20 minus t. 80 minus 20 minus t. That equals this mass times its acceleration, 40a. And we wonder, when we add the friction, does it change the tension? I might think it would, because there's going to be more friction on this front object than the back object. So won't this be held back more than that is? That might make me think the tension will be lower. Let's take a look at what happens. I'm going to use my same technique again of adding these equations, because I see I can eliminate t that way with a positive and a negative t. So I have t minus t, no t's, and I have 80 minus 20 is 60, minus 5 is 55. So 55 equals 50a. A now equals, divide both sides by 50, and I have 55 over 50. Or 1.1 meters per second squared. And of course I can plug that back into this equation to find out what the tension is. So t minus 5 is 10 times 1.1. T minus 5 is 10 times 1.1 is 11. Now add 5 to both sides, and hey, what happened? My tension is 16 newtons, even though I have friction. So the friction lowered the acceleration from 1.6 to 1.1, but the tension is just the same. So it turns out, because the friction affects each object in proportion to its own inertia, the tension that couples the two together is unaffected. And that's how we solve a problem with two masses coupled by tension.